the knapsack problem. Now, this is one of those classic problems that you will see in school, right? Even from a very sort of early level. When you first learn about recursion, this is one of those intermediate things that you'll have to attempt, right? Above generating Fibonacci numbers. So today, let's take a look at, well, what exactly the knapsack problem is and how we can solve it. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. So today we'll be talking about the knapsack problem, which, while on the surface sounds fairly simple, it actually has a lot of depth. So we will be breaking down this video into several parts. First off, I'll be describing to you exactly what the knapsack problem is. We'll then move on to take a look at why we can't solve it using a straightforward method. We will then look into the thought process, the rationale behind the solution, before actually implementing it in Python. Towards the end of the episode, we will be looking at variants of the problem, as well as solutions using dynamic programming, which is of course, the next step up. So, that is a brief overview. You will find timestamps in the video description, so yeah, if you want to skip ahead, you can pop it open. The timestamps should be there. If they're not, send me an angry comment. Well, hopefully not too angry. Anyway, let's jump into the basics behind the problem. While many variants of this so-called problem definition actually exist, I'm going to be talking about the most classic one of the lot, and that is you have a knapsack. You have a backpack that you want to pack, and the idea is you have a weight limit, right? You can't pack too much, otherwise you can't carry the bag. So that is one constraint. However, on top of this, all the items you get to choose from, whether you want to pack it or not, have some kind of monetary value associated with it. What you want to do is to maximize the value of the items you've selected, while at the same time not going over that weight limit. So as you can see, this is a fairly interesting problem, and if you look deeper into it, it's more challenging than it seems. The most important conclusion we have to draw from this is that a greedy solution will not work. Now, a brief explanation of what greedy means. When you have a selection problem like this, a greedy solution involves, making a good choice, picking an item, and basically sticking to that item. There is no notion of saying, I'm going to pick this item now. Later on down the line, if I realize that, not picking this item would have given me a better result, I will let go of it, right? I will just drop it and pick something else. There's no notion of this in a greedy algorithm. This particular problem cannot be solved in a greedy manner. Since we have two very different conditions here, you'll find that it's not so straightforward as to what you can pick and what you cannot. Long story short, if you were to sort of pick an item early on that seems like a good choice, you limit the number of possible solutions you can reach from that point, and that may cause you to, miss out on an optimal solution. Instead, what we are going to have to do is we're going to have to basically look at every single possibility, every single combination of items that we can select, and out of the lot, pick the one that works the best. This particular pattern that is exhausting every possible combination of something, turns out to be quite easily solvable by using recursion. In fact, that is the key learning points behind the knapsack problem. It is a way to exercise your understanding of recursion. Recursion comes in extremely useful here because not only can you easily explore every possible combination, you are also able to, basically retract your way back and pick the best of the lot. So I know this isn't very clear to understand in words, so let's take a look at some pictures and we'll see, a better representation of how all this is going to work out. Let's take a look. So here is how we're going to approach solving this problem, at least recursively. There are actually two parts to this. Firstly, we do need to find out all possible combinations of items that we could pack into our knapsack. So generating this would be the first part of our task, and as it turns out, that is a problem in and of itself. Of course, once we have this, we can use the solution of this part to evaluate and choose the best combination of items, such that, we stick to the correct weight and maximize the value. So let's look at our first half first. Essentially, what we're trying to do is we're trying to generate a power set. To demonstrate this to you, we're gonna just stick to 3 items first. We're not gonna think about weights or values. Instead, let's just try to generate a power set. And that is, if you have a set of items, its power set is a bigger set that contains all possible combinations of the items. Let's see how we can build this with recursion. We start with a recursive function call. What it's gonna do is, well, it has an input of several items, and through recursion, right through doing a series of recursive steps, we want to end up seeing every possible combination of these items it has been given. Here's how we start. We start by looking at the first item of the lot. We then make 2 recursive calls, the first of which has the item selected, and the second does not. I like to call this the switch on, switch off pattern. So yeah, our current item is A, we make 2 recursive calls, one with A switched on, one with A switched off. Let's try this again. Let's say for this recursive call, we are of course now looking at the item B. Again, we generate 2 recursive calls, switch on, switch off. So essentially, that's what we are doing the entire way. Notice how our input list diminishes with each recursive call. And yeah, that is why each recursive call can simply operate on the first item it sees. Let's try this one last time with this recursive call down here. Again, on item B, switch on, switch off. So yeah, because these are recursive calls, no matter how many input items there are, we will be able to generate, well, a full list of every possible combination of A, B, and C. So this is a great first step in solving our knapsack problem. Of course, if you remember our original formulation of this problem, we had 4 items, and as you can imagine, things get a little bit more complex. That's right, there is this explosion of possibilities. Every single item I add, the tree doubles in size. We have to do twice as much work for every item we add. So yeah, this is not going to be an efficient algorithm. But let's put that aside for now, and let's try to see why exactly we want to do things this way. Well, as it turns out, when we have enumerated all possible combinations, we can start to assess them. When we have a set of items, we can easily tell its value as well as its weight. And this is going to help us in making our decisions, in basically picking and choosing the combination that works best for us. Let's see how this works by zooming into just one part of the computation. And let's just look at this tiny little subtree here. Now, in the case of this little computational step, we are switching D on and off. As you can see, both of these stay under the weight limit, so both of these are valid solutions. Of course, validity isn't enough here, we want optimization, but as it turns out, because this guy here has made these 2 recursive calls, we can simply pass the results back. Each instance here can simply return the value and the weight, and well, what this instance is going to do is it's going to compare the 2 and make a judgment call as to which one to keep. Of course, in this case, well, we want to keep this one because, well, it has a better value and it stays under the weight limit. So not only is it a valid answer, it is the better of these 2, and that is why we keep it. Let's zoom into another part. Let's say this particular subtree here. Now, this one is even easier to process because, well, this particular instance has overshot the weight limit. As much as the value is good, we couldn't possibly pick this because we have failed one part of the computation. As a result, this becomes even easier. We simply pick the other option, which, well, stays under the weight limit. And guess what? By just solving these 2 subtrees, we actually have the solution to this subtree. Previously, this guy has made 2 recursive calls and they've gone ahead to make their own recursive calls. But at this point of time, those have been complete. Each one of these have an answer to present. And again, this is recursion, so it's going to perform the exact same logic. In this case, again, we're making a judgment call between 2 sets of values and weights. Well, this guy is better, so we pick it. Now, imagine this happening at a bigger scale, across every single function call. And that's essentially how we solve the problem. So let's see this whole thing in action. But before that, let me show you one more thing. As it turns out, we do not actually have to generate the entire tree. For example, in this case, if we have A, B, and C, regardless of whether D is chosen or not, we have already gone over the weight limit. There is no point doing any further computation because both of these results we know for sure will be invalid. As a result, we don't bother. Even if we're not at the end of the computation, but if that particular step already goes over weight, we simply stop. There is no good answer that can come out from here, right? So we find that we do this twice, one up here, one up here. And while we have several other instances of, particular combinations going over weight, we don't get a chance to cut them off early because they happen right at the end of the recursion anyway. But yeah, this has been our tree. We have started from nothing, we have moved all the way to enumerate all the combinations, well, minus the ones that definitely don't work. And now we can start to extract our results. Clearly, those that go overweight can be immediately eliminated. For those that are fine, we will pick the more optimized of the two. So there's one instance here, and one down here. The results go back to the previous instances, and we repeat the same procedure again. Of course, in these cases, we still have several overweight items, so it's a no-brainer, we can only pick one. But in these cases, it's still fine. We just pick the better of the two answers. The values are returned, and again, we'll repeat that process. Pick the better of the two answers, and return. We are now down to our final step, and again, we make our choice. In this case, we have narrowed things down to, two of the best solutions there are. Of course, since they're not the same, this is better, and so that will be the result of our final computation. We can only pick the items B and D. That maximizes our value while staying under the weight limit. So that, ladies and gentlemen, is what the recursion is going to do to allow us to, find the answer. Starting from a single point, we'll branch out, we'll visit every possibility, and as we retract our way back, we'll filter out the not as optimal answers, and we'll end up with the best of the lot. Hopefully this has been a clear picture. What we're going to do now is we're going to write a little bit of Python code to solve this problem. Let's take a look at how this works out. So alright, let us get started with our code, and the first thing we're going to implement are, the couple of things that we've already seen in the slides. Firstly, the weight limit, right? We are going to carry a maximum weight of 5, and these are the values and weights represented in two parallel lists. So item 0, right, same index, it has this value, it has this weight. And yeah, so on for the others. With this, we can begin by building our knapsack function. So it starts off like this, right? We'll define our knapsack function, and it's going to take in two parameters. Firstly, a position, which represents the item we are currently looking at, as well as a selected list. This tells us the items we have selected. Right, so this is a list that will contain the indices of the items that have been selected up to this point. Now, with every bit of recursion, we should always start off thinking of our base case, right? And we'll get to the recursive case later on. Remember how our code branches out. Essentially, there are only two times in which we stop. Firstly, we'll stop when there are no items left. So this is our first base case, right? When we're looking at the very last item, obviously we couldn't continue on. Now, remember, since the position actually keeps track of, the current item we're looking at, so this is the index of the current item. So as long as this position actually overshoots the length of either of our inputs, let's say we use the weight, then of course we are done. But what do we give back? We have to be pretty strategic about what we give back, right? Because essentially, we have to mention the two things. Again, cast your mind back to the diagram from earlier on. We have to give back the value as well as the weight. So how we're going to do this is we're going to give it back as a tuple, right? It's essentially just a collection of two items. Essentially, we need to give back the total value as well as the total weight. Of course, we're going to have to populate these two variables, right? So we're going to calculate these values first. Let's create a part up here that calculates totals. We start off with, our two variables set to 0. And what we're going to do is we're going to loop through our list of selected items. Now, remember, selected is a list of indices. So basically, whatever you see in here, right, are our selected items. And we'll use these values to actually read, right, to actually query from our two original data lists. So, to calculate the totals, essentially we will look at each selected item we have, right? I represents the index, and we simply add on the values. The total value will increase by the value of the current selected item that we are looking at. Same idea for the weights. So let's go ahead and add that part in as well, like so. So yeah, essentially we're going through the selected list, pulling out the value and weights of each selected item, and accumulating them into our total value and total weight variables. With this, we can return these two variables, right? And the previous function call will do the right thing, right? It will look into the value and make its decision. Clearly, this isn't the only base case. Remember what we said earlier? If we basically run overweight, right, we don't have to go further. So essentially, we can also stop if overweight. And essentially how we do that is extremely simple. We check the total weight that we have calculated up to this point. If it exceeds the weight limit that we have set above, we don't have to do anything else. In fact, what I'm going to do is I'm going to return 0, 0. Now, there is a reason why I do this. Essentially, we don't bother with any of this, right? We return 0, 0 to signal that this isn't going to be a valid answer. Since the value is 0, it's essentially never going to be picked. Unless, of course, all other choices are even worse. So with this, we're ready now to proceed on to our recursive case. This is extremely simple. We want to make a recursive call to Knapsack. Our first parameter is the position. Again, cast your mind back to the diagram. Essentially, we can look at everything except the item that will be checked in this current iteration. And what that means is, we want to look at position plus 1. In other words, we want to look at the next item. We move on to create our second parameter, which of course is our list of selected items. Now, let's do switch on first. So we'll take the existing list of selected items, and we will add the current item to it. What we're creating here is essentially a bigger list that, well, contains all the current selected items as well as the current item. So this is switch on, right? So let's put a note here, switch on. Now, at the end of the day, this is going to return to us a tuple of values like this, right? So we want to create a variable to hold that, which we can use later on for comparison purposes. This is one of the two. So let's try and do this switch off case. Answer 2, right? So again, what we're doing is we're trying to get a second answer. No difference, we'll move on to the next position. But this time, what's different is we want to create a copy of the selected list. So the selected list is going to be exactly the same as the current case, right? Which essentially means we're taking our current object, but we are not including it in our selected list. In other words, this is the switch off case. Having to do copy here is just a little Python quirk. If you don't say that, you're referring to the exact list that is in here, and that could create some inconsistencies between each call, so you don't want to do that. But yeah, essentially, these are our two recursive calls. By this point, what we've done is we've explored both recursive subtrees, and we've come back with the relevant answers, answer 1 and answer 2. Our job at this point is to basically pick the better of the two answers. And in this case, thanks to the fact that, well, our weight limit has already been checked for us, all we need to do is to find the one with the greater value and return that. So, if answer 1, position 0, right, that would be the value itself. If that is greater than the value coming back from answer 2, like so, then we would return answer 1, right? We'll basically pass back the better of the two answers. Else, we would return answer 2. It's as simple as that. We return the greater of the two. With this, we are done with the entire function call. At the end of the day, what I'm going to do is I'm going to, well, go like this, answer equals to Knapsack, right? I'll call my function. We'll start at position 0 and we'll give it an empty list to build the selected list. At the end, print answer. Now, right before I run my code, I've actually spotted a little error here. Now, this one is very subtle, so it's an interesting sort of learning, opportunity here. Notice what happens. We're checking to see if we're at the end first, before we're checking to see if we've actually gone over the weight limit. This seems to be fine, right? These are two tests that are kind of independent of each other. But in fact, we do need to check the latter first. So I'm going to swap the order here. Here's why we need to do that. What happens is if we end up in a place in which it's both the last item and it goes overweight, we must do it in this order. Otherwise, we'll get the values going back, right? Returned as a correct, valid solution. And we don't want that. So yeah, correction, right? My mistake, sorry about that. Now that we've swapped these two cases around, let's go ahead and run our code. So here I am in my console window, right? Let's go ahead and say Python, run this file. And the answer we get back is 17.5. Remember, the first number is our value, our maximized value, and our second number is the weight. In this case, this is the answer that we have found by manually tracing the knapsack problem, right? When we actually looked through our tree, we realized that this should have been the best answer. And indeed, our code gives that to us. So yeah, it was able to do the computation we expect. And there you go, that is the solution for the classic knapsack problem. Now, as it turns out, there are many variants of this problem, and well, they can be solved in a similar manner, but we will have to sort of tweak things a little bit here and there. For example, one particular variant of this is that, well, there isn't just one of each item. Maybe you are trying to buy things off a shelf, and what that means is you may be able to pick multiples of a particular item, if that actually gives you a better result. This complicates things a little bit, because essentially what we have to do is not only do we, switch an item on and off like we did earlier on, we'll have to consider what happens when we pick 0 of the item, that is of course the same as switching off, and then we'll need to consider what happens if we do 1 item, 2 items, 3 items, so on and so forth, and basically we stop only when we exhaust the weight limit. So instead of switching an item on and off, we now have a bunch of possibilities per step. Each one of these possibilities then branch out even further. For the second item, we'll have to consider 0, 1, 2, and so on as well. And we'll have to repeat this basically for every single item we can select from. As you can imagine, that makes the recursion even more complex, right? That makes the whole tree of possibilities even larger. So yeah, regardless, as it turns out, all this can be approached with the classic recursive solution. But while this strategy is sound, it is in fact not all that efficient. Let's take a look at why. Now, if we have one item, we only have 2 outcomes to deal with, right? That item is either switched on or off. When we add one more item to it, we end up with 4 outcomes instead. That is basically all the combinations in which these 2 items can be switched on and off. What we've just seen is a doubling of the total number of outcomes. When we add another item, this doubling happens again. We now have 8 different outcomes to deal with. And essentially what this means is we have 2 to the power of n outcomes given n items. Even as n gets just slightly larger, 2 to the power of n is going to get huge. And yeah, that means this algorithm is going to have problems scaling up. And that is why, even though this is an intuitive way to solve the knapsack problem, it's not an actual practical solution. Instead, we look to its counterpart, which makes use of dynamic programming. What makes the dynamic programming solution work is a memo table. It uses a technique called memoization. And by essentially laying things out in a table form like this, we keep track of any repeated computation so we don't have to redo it. This is a very simplified explanation of what DP actually is, and it's definitely not representative of the subject. So if you want to find out more, check out the card on screen. Right, we've done episodes on dynamic programming before. I'm going to gloss over a lot of the dynamic programming theory here, and instead we'll just focus on how we solve the knapsack problem. So here's how it works. Our memo table actually keeps track of information along 2 axes. The horizontal axis represents weights. We start from 0 weight, no weight at all, and we increase all the way up till the maximum weight. The vertical axis refers to the items. as we move down each row, we are considering more and more items. What we actually store within the table itself are the values. So for a certain weight limit and for a certain number of items considered, the best value we could possibly get is stored in the corresponding square. So yeah, to make this simple, we essentially have a table which has a width of max weight plus 1 and a height of number of items plus 1. Why we need these two plus 1s is because we have to take care of the case in which there is nothing. This column is 0 weight and this row is no items considered. We need this as a sort of jump off point for us to build everything else. Here's a general idea behind how the memo table will work. We start off at the upper left, and what we do is we fill in the squares going downwards from left to right. How we fill in each square is surprisingly similar to the switch on, switch off method that we've seen in a recursive step. To see this in action, let's assume that we have already explored these rows right up till this point, and yeah, these rows will come later on. So what that means is we're currently looking at this square, and we're deciding what value to put in it. Here's the deal. This particular column has a weight limit, right, according to how we label our columns. And this particular column has a weight limit of 3. Now, at the simplest case, we simply switch off. This happens when the item we're currently looking at, that is this particular item represented by this row, has a weight that is too big for this particular square. In this case, we have no choice but to switch off. Of course, if that is not the case, then we have to have more considerations. Essentially, if an item can be switched on, we need to do a little bit of checking. Let's say the new item we want to add has a weight of 2. Since this column has a limit of 3, this item can certainly possibly be considered here. The idea is this. If we do include this item, we don't want to exceed the column weight of 3. So what does that mean? That means that if we do want to consider this item, then everything else we have on this square can have a maximum weight of 1. That, ladies and gentlemen, is why we take a look at the column, right, representing the weight 1. How we approach this is, in the previous iteration, right, at this particular point, what we've done is we've considered these two items so far, and we have a maximum weight limit of 1. This is the best value. What I can then do is I can consider the best value at this point and add the value of the new item. This tells us the best value we can get if we switch on at this point. Obviously, that's not the only thing we have to consider. We also have to consider the switch off case. So yeah, we basically take the maximum of the two. This is the best value I can get if my new item is switched off. This plus this is the best value I could get if the new item is switched on. I pick the maximum of the two, and what I get in here at the end of the day is the best value I could possibly get, given the weight limit of this column, and given the fact that I've taken a look at the first two items here, right? This row corresponds to no items at all. So yeah, that is the idea. As we move forward, we are accumulating the best values we could see. By doing that, as we are computing each new box, we can refer to the best answers we've had so far, and basically add on to that, to get a better answer on top of the best answers we've already had up to that point. Hopefully this paints an okay picture of how the dynamic programming approach works, but what we're going to do is we're going to simply trace this using the example we've already seen multiple times. Since we have 4 items and a maximum weight of 5, we have a table that is 6 by 5, right? So the horizontal dimensions is the maximum weight plus 1, therefore it's 6. The vertical dimension is the number of items we have. The vertical dimension is the number of items we have plus 1. And that is why we have 5 rows. Let's go ahead and fill in our boxes one by one. Now, the first row is very easy. We start off with nothing selected. Of course, the value is going to be 0 all the way. This allows us to look at the first row, which is where we decide whether we want to use the first item or not. Of course, the first column is extremely straightforward. In this case, because we have a weight limit of 0, we can't select this item. We can only switch off, and therefore, well, the value at this point is 0. Now, the weight of this item is 1, and therefore for this column, we could choose this item. In fact, the same deal for all other columns. In this case, we don't really have to think too much about comparisons because a value of 3 is definitely better than a value of 0. So yeah, this step is kind of a no-brainer, right? We just pick this item, it's switched on throughout. Of course, under the hood, all the computation still happens. But for our trace, we will keep things simple by just filling in all the squares. And that allows us to move on to the next row. So yep, essentially we're looking at item 2 now. Of course, we have a value of 0 if our maximum weight is 0. Nothing new here. Let's move on to talk about the other squares. Now, first of all, the weight of this item is 3. Therefore, for the columns 1 and 2, there is no way we can actually pick this item. We must use the existing values that we already have. But moving forward is where things start to get interesting. Now, over here, the weight is 3, and therefore we have to make a judgment call. Do we switch off and simply make use of the old weight, which is 3, or do we try and switch it on? If we want to switch it on, we have to think about which value to use, and in this case it would be this square. You see, the weight here is 3, so there's no way I could actually include, well, our item 1, right? Because that overshoots the weight limit. Therefore, it's a judgment call between whether we want a value of 3 or whether we want a value of 9 plus 0. Obviously, 9 wins out. So yeah, that's essentially the decision-making process. Now, let's try this again for the next square. Again, this is a judgment call between switching off, which has a value of 3, or switching on, which has a value of 9 plus 3. Obviously, the latter is higher, which is why we switch on. We get 12 for this square, and in fact, because the math, comes out the same for the next square, we fill that in as well with 12. So yeah, we have a more interesting row now, right? This particular row has a few different outcomes, depending on the current weight limit, right, of the column we're looking at, as well as the values that have been accumulated up till this point. So in fact, what we've seen here is the full behavior of this algorithm, but for the sake of completeness, let's trace this through to the end. Our next row, of course, represents our next item. Now, this has a weight of 4, and what this means is, as long as the column has a weight less than 4, we don't have to think much. We just use the value that's already there, because there's no way we can switch this item on. For the next column, we actually have a way up between 12 and 0 plus 12. Again, the reason why we're checking this particular square is because the weight is 4. We start off here and we count our way backwards. 1, 2, 3, 4, and we end up here. The only value we can consider for this column, right, with a weight limit of 4, is this guy. Now, as it turns out, in this case, we have a tie. And it doesn't really matter which one we pick, because at the end of the day, we still end up with 12. Of course, the next square is where we make progress. It's a way up between 12 versus 3 plus 12. We now get a bigger number than we've seen up to this point. 15. So that's great, and hopefully you can see how we are slowly progressing towards the optimal answer. Let's move on to our last row, which considers the last of the 4 objects. Because it has a weight of 2, we don't have to do much for columns 0 and 1. Of course, over here, we now make the judgment call. 8 plus 0 versus 3. Obviously, we keep 8. We come down here again, 8 plus 3 versus 9. Obviously, we pick 11. Again, we move on to our next column, right? 8 plus 3 versus 12. Now, this one is interesting because actually 12 is bigger. Switch off actually gives us a better solution than switch on, thanks to the fact that our weights are limited. That is why we actually keep this value. We keep 12 instead. Again, moving on to our last square, is a way up between 15 versus 8 plus 9. Clearly 8 plus 9 is better, it gives us 17. And in fact, this is the result we've seen earlier on. 17 is the very best weight we could get, given the weight limit of 5. This has been the dynamic programming solution to the knapsack problem. And in fact, if you sort of paid attention to how I did this, notice how the recursion actually disappears. Yes, in fact, what we're doing is we're simply doing a pass through a 2-dimensional array. In fact, we can see the number of operations we have done by just looking at the size of the table. since we are visiting each square once, really the answer is just the width of the table multiplied by its height. What this means is this particular algorithm is n plus 1, right? N is the number of items plus 1, multiplied by the total weight plus 1. What this means is we've reduced our original knapsack problem, which has taken O 2 to the power of n time, down to just O n times W. What we've done is, instead of doing a whole lot of computation, we offload some of it to storage, and as a result, we end up doing a lot less, thanks to the fact that we could simply look up the answers we've gotten so far from storage. That is the power of dynamic programming, in this case applied to the knapsack problem. And that, ladies and gentlemen, has been an in-depth look at the knapsack problem. I hope you found this useful. We've basically taken a look at this problem from many different angles, right? Using a recursive as well as a dynamic programming solution, which of course actually strips away the recursion. That is basically all there is for this particular episode. I hope you found it useful. But yeah, until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.